Hello, everyone. My name is Felicia Graham, and I'm with the City of Dayton Department of Water. And I want to thank you for attending the Ohio Stormwater Association webinar. We're going to be talking about using the runoff reduction method to manage stormwater on development projects. And our speaker today is Justin Reinhart with Ohio EPA. Just a little information about the Ohio Stormwater Association. The association is dedicated to advancing the management of stormwater and related natural resources through education, leadership, water-based coordination, and technical assistance in Ohio. We have a board of directors. Our president is Kelly Kubander with Strand Associates. The vice president is Regina Collins with the City of Toledo. Our secretary is Teresa McGady with the City of Dayton, and our treasurer, Bob Lentz with Butler County Stormwater District, and our past president is Mark McCabe. We invite you to join the Stormwater Association, and you do that when you sign up to be a member of WAMO, the Water Management Association of Ohio, and you choose stormwater as your area of interest. We also would love for you to join a committee. We have several committees. Education committee is the committee that hosts the quarterly webinars. We also have marketing and membership, regulatory, transportation, industrial, and we have a new committee coming soon on extreme weather. If you are interested in continuing education units, or please make sure, we're going to put a link in the chat. You follow that link, you answer the questions that will be in the chat. Just make sure you answer them on that link and then submit that, that sheet back to WAMO, and we'll use that as your sort of proof of attendance, your attendance verification. And on today's agenda, we have Justin Reinhart. And Justin is an engineer with Ohio EPA's Division of Surface Water, where his role is to provide engineering assistance for the stormwater program. Justin maintains Ohio's Stormwater Manual, the rainwater and land development, as well as helps Ohio EPA staff and the local regulated community, consultants, and developers navigate technical elements of Ohio EPA's construction and small MS4 NPDES general permits. Justin gained 20 years of experience with agricultural and urban conservation practices while at the Department of Natural Resources and the Ohio Department of Agriculture. Prior to coming to Ohio EPA, Justin has a degree in civil engineering from the Ohio State University and is a registered professional engineer in Ohio. So Justin, welcome. And I will turn it over to you. Okay. Also, one other thing, you want to use the chat to pose any questions that you have for Justin, and then we will address those questions at the end of his presentation.
Okay, welcome everyone. Thank you, Felicia, for the introduction. It's always a bit painful hearing your own bio, but the thing that strikes me is that when I hear that 20 years, it starts to make me go, oh my goodness, what's going on here? So I hope everyone can see the screen I'm sharing, and we will get started with today's presentation using the runoff reduction method to manage stormwater on construction or development projects. Okay. So over the next 45 or so minutes, I'll cover a brief introduction to what is the runoff reduction method, take a closer look at some of the runoff reduction tools or practices, and we'll close out today discussing how it can be applied in some of the peculiarities and particular items required, etc., of if and when we can use the runoff reduction practices and runoff reduction method. As many of you know, are hopefully likely aware, the runoff reduction method was added to Ohio EPA's current the current stormwater construction general permit as a possible or potential tool to comply with post-construction stormwater management requirements. It also may be a viable option for some developments that are within the Big Darby Creek watershed, which is here in west central Ohio, that may need to mitigate groundwater recharge as outlined in Appendix A of the construction general permit. So here's the language on screen. It's very brief and it very nondescript in expressing that it has the potential to be used. The practices are listed and points you to the rainwater manual for further instruction. Over the course of the past few years since the permit renewal in 2018, we've slowly built to having all the pieces in place here now, and I think we're finally sailing forward, although probably some hiccups as we learn our way around this runoff reduction method. So what is the runoff reduction method? Well, it was developed again some 15 years ago here by the Center for Watershed Protection, primarily focused on work in the state of Virginia and their new stormwater regulations. In a nutshell, I mean, I think the easiest way to describe it is a creditable process or process for crediting a typical LID, meaning low impact development, or green infrastructure stormwater management approach. So many states have adopted it, other municipalities as well, and in some cases it's intertwined into almost mandatory requirements for on-site retention or green infrastructure in some areas. And while these concepts aren't really anything new in terms of green infrastructure or low impact development, what maybe was or is new to us is the process of how do we insert this into our regulatory framework. And what we mean when we say green infrastructure or LID or these practices is essentially using natural hydrologic processes other than strictly relying on detention to reduce the runoff volume as well as attenuate runoff flows. So I know natural, green, those kind of terms can sometimes have a bad connotation to them. And it's important to not necessarily think about the look of these practices as the intention, but understanding the hydrologic processes and the engineering that goes along with those processes. So how can we convey water in the sheet flow to shallow concentrated flow to open channel runoff model that we all have learned and utilized through various runoff hydrology calculations and models on every project? How do we take our conveyances and truly mimic that hydrologic model? Can we develop the initial abstraction that's incorporated into those models, or that initial loss of rainfall that does not get converted to runoff upland of the practices? Can we take advantage of utilizing soils to maximize the infiltration rates that are connected with those models for the type of soil and the land covers that go along with them? So these are the things we're trying to utilize, these internal built-in hydrologic tools, in order to design and place BMPs for stormwater management. Okay, so why is all that important, or what's the deal with significance to that thought process? What's good about it? Well, on a stormwater water quality side of things, consider two things. First of all, that added volume reduction brings with it the benefit of a reduced pollutant load. So while our primary BMPs are reliant on longer gravitational settling and retention times to capture suspended solids, and they work really well to do that, they're generally fairly ineffective at capturing dissolved pollutants. So as you can see on the right, to a kind of broken apart chart here from the International Stormwater Database, and the coding here, the symbology isn't important. It's to see, you see a lot of the black triangles versus the reds, which is telling you very good, and you see a lot of very bads, and just demonstrating that phosphates, nitrates, sodium chlorides, all of these dissolved pollutants aren't being captured well in our primary practices. So what do we do about that? Well, let's also take into consideration small storm hydrology, or the concept that the vast majority of our total volume of rainfall and runoff is produced in small events that happen dispersed across the year. If we add this up on a cumulative basis over the course of a year or any period of time, we can actually capture a lot of stormwater by capturing small events. And that whole model is built into the way we approach water quality, and most folks do. So if we take those two things into consideration, our best controls are for these dissolved pollutants, and along with it, to an extent, that the solids that come with stormwater are source control. Number one, just don't have the pollutant in the first place, and volume control, removing the runoff volume that we have to capture, treat, that's discharging from our site. So pointing backwards, the way we do that is to utilize those built-in hydrologic tools, that abstraction that occurs, infiltration, evapotranspiration within our practices. And that's, to an extent, the definition or concepts behind green infrastructure. So the question becomes, how do we make all this work? We have this great concept. Okay, that's all well and good. I like to do it. I want to do it. But how does it fit into this regulatory framework that we have, which is really modeled on a dated original concept of capture all the water coming from a site in a stormwater pond and size that pond to treat a knee of the curve runoff volume, or the water quality volume. And that's sort of our singular model. Well, we don't have a way until now to account for these losses. The runoff reduction method creates a currency, if you will, that allows those natural hydrologic processes to get some love, I guess, or I guess I mean credit there, and subtract that from what we're trying to treat and capture in that primary stormwater pond, or that stormwater BMP. So in a nutshell, it's taking those losses and making them synonymous or the same as or part of the treatment volume that we can get credit for. What does that look like in terms of maybe an example or some numbers? We'll take a traditionally designed paved area that you might see here on the left, and that has it's captured and treated in a traditional detention basin that's properly sized to the mandated water quality volume. And everything here that my consultant and MS4 friends are fully aware of and probably can do in their sleep by now. So it's fairly straightforward. You produce a water quality volume that's treated. Well, using the runoff reduction method or model, if we change our conveyance path around a bit such that runoff from that pavement area is allowed to sheet flow into a swale or an open channel type conveyance to direct it to that stormwater basin, we can get some good losses, abstraction, infiltration, as well as the treatment that occurs in the filtration of flow through those two areas. The runoff reduction method allows us to create a numerical credit that we can apply to the water quality volume, that mystical volume. And I say that because I think it's really neat how simple of a formula it is that we're given to come up with a treatment requirement, but that simplicity unfortunately doesn't always allow for all these flexibilities, such as how to account for these runoff volumes. So the runoff reduction process is just that real simple math process. Maybe we should call it a BMP reduction instead of a runoff reduction model to be a little bit more clear or more exact. I'm probably too late to go back and do that now. And we're also using, as I said, models and information that's been adopted and slowly been adopted in various parts of the country, in these states and municipalities. So that's a real quick, hopefully not too quick, introduction of what we're really trying to accomplish with the runoff reduction method in general terms. Just to clarify maybe some misconceptions that are out there, and get those off the table up front here. And at risk of being a little negative with all these knots that are bolded, it's not a reduction in runoff volume rate or the curve numbers from the pre-development conditions to the post conditions. I hear that a lot. It's not I'm reducing the runoff through my development process. This is post-development reduction. It doesn't apply to all pervious areas within a development. We're looking at utilizing these areas that we can direct stormwater runoff towards. So just by increasing the perviousness or decreasing the imperviousness, which is a very good thing in terms of the overall runoff quality, it doesn't necessarily allow us to use all that area for stormwater management. It may not be practical in all developments. In fact, most traditional designs, as I showed in that sort of simplistic example, may have challenges if there's not enough space, if there's not a willing partner, owner, developer. Risks are tolerable for that extra wetness, drainage, challenges that may be perceived real as far as ponding of water and things like that goes, where that water goes once it infiltrates, what is our substructure as far as utilities and foundations, etc. So those things are all going to come into play that may limit or even prohibit the runoff reduction method from being used. And of course, of highly impervious areas, we'll have a challenge to find that space in which to employ the practices. But there are some that are designed to be utilized in smaller spaces. It may not necessarily completely eliminate the need for primary or larger controls, stormwater detention ponds and basins, especially if they're peak discharge, which are requirements, which are obviously generally much more substantial in terms of volume than the water quality volume is. But it can certainly reduce the size of those practices, and in some cases may work to serve as a primary practice where we have small areas that aren't readily treatable in a much larger practice, like a detention basin that was made more in mind with a large acreage development. Orifice sizes and things like that can become problematic in these small areas. It also doesn't work too well if it's not planned well in advance. If it's not a directive at the beginning of the layout of the entire development and some of those planning stages. So again, some of that ties into the developers' desires and needs, and then also into where can we utilize some of the existing or planned pervious space. A number of the more recent applications have done a little bit more retroactively and trying to solve issues, the compliance issues with stormwater management, and that doesn't work as well at that point to design these practices and fit them in right up front, or I should say on the back end, as it does when they're done up front. So before we wrap up this introduction, just to geek out a little bit on the math for all the engineers in the room who like numbers and charts. Since I don't have a whole lot of them here, I have to fit a couple of them in. As I mentioned earlier, the concepts here aren't really new, but really this is a way to fit them into this hydraulic calculation oddity that is a water quality volume. And by oddity, I mean it's not a routable statistical sizing event based on risk tolerance that we generally do in our hydrologic engineering to size all of the rest of our stormwater infrastructure and our other development components. So what I'm pulled up here is just information from TR 55, the USDA urban hydrology guidance. And many of you are familiar with that process through the curve number methodology to devise runoff peak rates and volumes. And there's the method in there well, I should back up by saying that generally the assumption in urban areas is that impervious areas are directly connected. They're not disconnected into the pervious areas, but that water is separated from the pervious areas and directly connected to the outlet point. If it's not, there's figure 2.3 and I think it's 2.4 in there that give you guidance on calculating or modifying the curve number. So if you utilize that with that example I gave you before to adjust the runoff volumes for what might be, although this is an apples to apples sort of a comparable water quality volume event, you can see that the numbers in terms of percentage reductions are they're a little bit different than I just showed you in the previous slides, but they're really not that far off. And that is primarily because this method is assuming that an entire pervious area was part of the disconnection, whereas with the runoff reduction example I gave you earlier, we were only including half of the ground, the grass area, and the swale, and a small percentage. So if I kind of tried to make that apples to apples, you can see in my first asterisk there, the values of 74 and 37% here from that example I gave you really are pretty close. And maybe it's all just irony here, but at least tell you we're in the ballpark on this crediting system with other procedures for disconnecting impervious areas and using pervious spaces to maintain some natural hydrology. So again, don't get too caught up in those numbers, but I just wanted to lend maybe a little validity to the whole process and maybe paint some perspective on the fact that this isn't something coming like completely out of the blue or made up, but mirrors our existing hydrologic models. The one thing that maybe in going through this to make time here quickly didn't elaborate on, but is what's a key component of that is the soil, right? Now, what do we have as far as ability to infiltrate water? And part of that hydrologic model, all of you are aware, we have hydrologic soil groups. So we have all of our hundreds and hundreds of soil types or soil mapped units that are based on texture, depth to groundwater, depth to impervious layers such as bedrock, are all rammed into 4 very broad categories that give some crude estimation of how much rainfall is converted to runoff and how much is actually able to infiltrate and transmit through the soil profile. So we have our A, B, C, and D soils. What we did differently than that model is broke that down or bundled those into really just two soil types. The A and B soil groupings will receive, as you'll see here soon, a higher credit value versus the clay E or more restrictive C and D soils. And of course, for our standard practices, the ABC soils are also where we're looking to really push stormwater into the ground and utilize that infiltration as a treatment mechanism, not just opportunistically, but for the primary or the entire volume of runoff or water quality volume for a site. And a challenge with all of this is also recognized in this NRCS-based, SCS-based hydrologic model is that this soil information, soil data, and these soil groups were all developed generally with rural/agricultural soils and don't maybe necessarily fully reflect urban soils. And by urban soils, we're talking about soils that have been degraded through construction activities, compaction, removal of topsoils. So how do we remedy that? And we'll talk about that here too as we go through the credits and apply them a little bit more specifically. Okay, so that was a whirlwind, but hopefully just a quick introduction to the runoff reduction method and what really the intentions are, because I think it's important for us when we apply these to not just look at it as sort of an isolated view, but understand what is the point of what we're trying to do here. And I think that will help us understand better how we can apply and how we should be applying the practices individually. So let's look at those a little bit in more detail, more specifically. 2018, we introduced some provisional standards as the runoff reduction method was incorporated into the construction general permit. Finally have those in final form. Almost about a year ago, they were put into the slowly revamped rainwater and land development manual, as you can see here on the right, and are available online. These are the primary primarily they're conveyance practices that provide the runoff reduction credits. So the ones I highlighted here in yellow are the ones that we'll focus on. Rainwater harvesting is an option as pulling water off the store for a particular use, like a greenhouse or vehicle washing. It's a very specialized practice that I'm happy to talk with you about if you have a specific installation opportunity there. Very, very seldom used, obviously very beneficial, provided there's a strong demand for that water and dependable demand. So again, probably isolate the very specific industries. And then the standard table 4B infiltration practices are there as far as the standards go in the manual and slowly being updated. And the application here in terms of runoff reduction really comes in the ability to mitigate groundwater recharge in the Big Darby Creek watershed area, in that we can now apply, we can also transition that infiltrating water credit from treatment to groundwater recharge as well. So again, that was incorporated into the permit. The credit values and all of the design criteria are established in these practice standards, and we'll look through them here in some brief detail. And again, I have a couple spots on here I mentioned, but I point you to go back to the standards and look at those, read through those. I don't want to, and I can't capture every specific item in our short time here. But the point is to highlight a few things and get you thinking about their use and how they work in our design. So let's start with the basic impervious surface disconnection concept. So again, we're just taking runoff from impervious surfaces and redirecting it, spreading it over over a pervious area, using that as an opportunistic way to provide some filtering and infiltration of what will probably be small quantities of runoff, as you'll see by the credits. So this is ideal for very small drainage areas, small isolated pockets. It really is a dispersed type practice. It's not something that we can funnel all our water to. It's more about the concept of just removing the barrier, the curbing, piping, whatnot between the impervious and pervious area. Where their space is restricted, there's a possible to kind of go upwards instead of outwards and look more to like a rain garden or a stormwater planter, where we can actually not just flow water through an area, but we could stack it up at least to a very shallow volume, provide some storage, and thereby decrease the area needed for a disconnection practice. So these will be generally sort of low end practices. They can really serve well as multifunctional areas, yards, play areas, landscaping, etc. What is probably the most confusing element is that the credits are attached to the size of the grass area, or what we've called the receiving grass area, the grass cover that is receiving stormwater from the impervious surface. So that's where the credits are established. How much area do I have? And then, of course, as we mentioned, what are the soil conditions for that area? So that could be just sheet flow running off a pavement area, as shown on the lower left. If necessary or desired, it could go through curb cuts that allow the disconnection to happen. It sort of semi-concentrates things. And what gets different about that, as well as a downspout disconnection from a roof, is we've got these little concentrated areas that we need to redistribute. So if we have a grass receiving area that's relatively flat, open, generally the assumption is that that water will be allowed to fan out, as I sort of show in the dotted lines on the graphics to your right there. But we can't always figure out where that's going to be and go. So water's not going to cascade evenly and smoothly off the roof like you might see on a house and flow perfectly evenly through that grass area. So we have to sort of make a couple of jumps here in to make this calculable in defining a grass area with a simple width and length being in the direction of flow, that we can then attribute that unit credit towards. So there's an understanding. Here's the point that these areas aren't exact. Don't think that we're expecting runoff to flow in this nice even box. We're going to win some areas, lose some areas, but ultimately it gives us a good representation, I think. The credit values are listed there in the rainwater and land development standard. And as I mentioned, they're broken down by the soil group A or B for that grass area, or C and D, which would have a lesser credit, obviously a tighter soil, infiltrating less water, as well as a third here criteria for restored soil. So we're doing this under the expectation that our infiltration rates are probably less than ideal because those areas have been impacted through construction. We can give credit to raise that if we have that grass area back to its or sort of an idealized condition through a soil restoration process. And that is in our soil restoration standard. I don't know if that's the right term. I know soil restoration seems to apply something different, so I really like to focus more on the two tiers in that standard, the first of which is topsoil replacement, which is essentially stripping that upper layer of high quality, loamy, organic topsoil and replacing it, spreading it back on the area after construction is complete, which involves an intermediate process of some mixing that needs to occur to alleviate that light compaction and sealing, so you don't have sort of a stratified soil, as you can see through the step-by-step process here in the rainwater land development graphic from A, B, C, and D, where we have topsoil is existing, it's removed for our grading work, then we have that area broken up and the topsoil replaced to a level that can support a healthy vegetation. The standard also gives a specification for that that's not so much performance-based, they're method-based, that we can look to try and meet this in terms of what should that soil look like that is in that grass receiving area to be of the quality we're looking for. And all that is reflective of trying to recreate, mimic what's really a generally natural soil situation of as you can see from the table on the right here, that looking at just a handful of our primary or some of the key soil types in the state, that top upper 7, 8, 9 inches in a very silt loam condition with a high organic content that can really support a rooting environment. So a key component here will be, as shown in the picture, stockpiling that topsoil for later use. The design, again, these are relatively simple. It's a little bit of an accounting process, but it is also important that we have these criteria because we don't want to design something that's going to pond water, flood, create drainage issues, create structural damage, and also will work, which is maintain a sheet flow, won't be erosive and concentrate. So there are some limitations on the area as far as how much impervious drainage area there can be. Also, the minimum length, although any disconnection will provide probably good value for purposes of this sort of a credit accounting, there's a range of 10 to 100 feet that's effective area. They need to be flat, and this is sort of contradictory to our drainage principles of let's move water. Well, we want to move water just slowly, so there's a stipulation in here to have that first 10 feet flat before we start to send water away at a steeper slope. we'll see. This is probably one of the sticking points, and again, because it so defies some of our traditional grading, how we can make this work, if there's an improvement to be had here for some adjustments in the future. But again, the point here is to make sure that we actually have a sheet flow scenario. And as I mentioned here, for residential areas, this gets a lot harder to predict where water's going, and it sort of becomes a little bit of an estimate of, because we may not know where homes are going to be eventually built, and there's some reasonable estimates we'll talk about here in an example that need to be made. And also, how do we then in the residential setting assure that this continues when we have multiple plans, such as like a home architectural plan, a development plan, a home builder, a developer, a home buyer may or may not be present at the time. And how do we communicate that these homes are going to have disconnected downspouts? So that we chose not to specify means in these standards, in order to provide the flexibility to allow that to occur as what is probably the most best and efficient way, with a recommendation that these be at least shown on the subdivision plats. Okay. And again, thanks for the question. If you have any, please type them in. I'll try and address them if I can while we're hot on the topic, rather than waiting to the end. If I have an A or B soil with new topsoil, the credits additive 0.4 for AB soil and 0.4 for this topsoil. No, that will just be, and you'll see as we apply this later, that will be the unit credit volume that you use to come up with a volume based on the area of the receiving area. So you'll be taking 100 square feet times a credit to come up with what you can subtract from the water quality volume, and that you'll plug in either of the three, really two, possible values. So we'll walk through an example here towards the end of the day. Okay, disconnections are also great for establishing sheet flow to some of the other practices. So we talked about some of the concepts here are trying to stack these practices. So spreading water out through a receiving grass area, then putting it into a filter strip or a grass swale, like I showed in that simplistic example earlier. Practice-wise, the next step up looks very similar, but is we call it sheet flow to a grass filter strip in this case. So the thinking here is, again, same premise, same concepts: disconnection to an area of grass cover, managed grass, but generally in this case we're looking at it being a much more substantial, which isn't much, removing off the impervious disconnection area in terms of having a healthy soil and being a much larger area. So the process here is similar in that we're disconnecting the impervious, sheet flowing it across the managed grass area at a reasonable slope so that we can maintain sheet flow before it goes to a primary BMP, or in this case, as the drawing or the photo shows on the right, into a storm drain that will convey it to a practice. It's a good example, of what a grass filter strip might look like, recognizing that these aren't going to be, there will need to be accommodations for things like the handicap parking sign. Trees, probably not the best. I mean, ultimately it doesn't take up much space, but when this grows, with shading, leaf drop, etc., be issues or detrimental to the filter strip. So for now, I think that's allowable, but if we're seeing more than some minimal landscaping, it might be more the next topic. Again, length is in terms of the direction of flow, the width is along the pavement edge, and flow should be broken up from the pavement. And here's a great example where you can see the shadow in this retrofit situation where they removed the parking block or wheel stop. They have a walkway here, which also aids in making sure that flow stays as sheet flow, and a gravel verge. And the verge is that just gravel rumble strip, if you will. It can be important because it does a number of things. The sidewalk does too. They prevent damming that can occur if you have a sort of a pervious impervious meeting at grade. and then you end up seeing this on my house. We have this on our sidewalk. Water will pond in heavy rains on the sidewalk because it's dammed or blocked by the grass, which is now raised above our old sunken sidewalk. Likewise, if there's too much of a drop, if the pavement has a very large edge or raised edge, that flow cascades down, picks up a little velocity. It's on soil, starts to erode, and all of a sudden we start to concentrate flow, have issues. The drop is further. You've got a safety barrier, a visual barrier. That also maybe gives you a little protection from vehicles that might overshoot the edge of pavement. Those areas that might get shadowed, or some spillage of other pollutants from the engine block, I guess. Okay, I see some more questions. I'll try and keep moving here on these to move us along, as I'm tight for time, and hopefully get to answer the questions here towards the end. Real quickly, can you disconnect your downspout and run it to a roadside ditch? Well, yeah, I mean, yes, if you're following the concepts, you could utilize it for treatment credits. That's possible. If with the neighbor damming up the ditch, that's now you're starting to get into drainage laws, drainage requirements, and that's probably a whole nother topic for another day, and perhaps other staff. But we can talk about that further, Justin, if you'd like, at any time. Okay. So as I said, if you got a lot of trees in that area, well, now we're starting to get into the third tier, sort of the highest credit you can get in these areas, which is a conservation area. In other words, an unmaintained area, not of a turf grass, but now with woodland cover, meadow cover, prairie grass type cover. We've got high quality land cover that's capable of slowing, storing, and distracting a higher volume of runoff. You can see this might be an area that's part of a purchased property, would be ideal to maintain as a conservation area. You can see the ponding water in these areas that generally have very high quality topsoil because of all the organic matter that's introduced, the massive root clusters here. Don't need to go into great detail to say there's a lot of good that can happen here. So hence there's a higher credit associated for directing water into these areas that are unmaintained. The overall sizing concept is pretty much the same as the grass filter strip. It's expected that these are ungraded, undisturbed, unmaintained areas, with the recognition there are going to be things, perhaps a utility line needs to come through here, or some cleanup work needs to be done. Is it possible to build one? Yes. It's just, how long is it going to take to grow that? You know, these maples and sycamores to have this much girth and volume and mass, and so that evolutionary process probably starts with prairie plantings that then become unmaintained, and woody vegetation is allowed to occur. Again, you see the higher credits as opposed to just the straightforward, simplistic disconnection for both of these. The difference here is that the filter strips, because we're expecting a higher quality, now are associated more with doing the topsoil replacement for the standard credits, or upgrading to that second tier in the soil restoration spec to include soil decompaction, subsoil decompaction. And what that looks like is essentially the same thing. The graphic here from the rainwater manual looks very similar, except in the middle, part C, there is a subsoiling or subsoil decompaction step, which can be done in probably a number of different methods using what would be more common agricultural tillage equipment. That the point there is to break up that massively compacted clay subsoil and make sure that we truly have an impervious soil profile. If we skip that step and move straight from B to E, what we'll have is soup over concrete. Water will sit, not be able to infiltrate. You'll have a stratified zone, and that organic-y, hummocky topsoil will then become very soft, and vegetation will become saturated, pore space will be lost to water, and a myriad of problems there. So that's why that step is key in these conditions, where we have, as you can see here, severely graded and well-traveled, compacted, highly compacted subsoil. Almost looks like concrete there when it's wet. Does the conservation area need to have some type of protection, such as an easement? We backed off some of that language in general, but the thought for conservation areas was, yes, that there something needs to be, an instrument needs to be in place to ensure that that area is not maintained, because it would easily be degraded to manage turf at some point, and we're also giving a much higher credit to it. There's sort of an expectation with the impervious surface disconnections that it's sort of unpoliceable. These areas may move with time. You can't prevent people from building a deck or swimming pool. Doesn't mean that water's not going to eventually have other grass to go to. But there's sort of an expectation. There's a win loss that probably will occur, and there's so much to be gained that we really can't put those stipulations on it. But the grass filter strips, a little bit less of an issue because they're maintained as a pervious area, but they should be, the conservation area should be somehow protected. And okay, another question here on salt water. I mean, that's kind of, again, that ties to everything. Do we start concentrating sodium concentrations in our stormwater BMPs? And that's a $24 million question right now. How do we deal with road salts, and what are the ramifications of it? And those are questions that are being asked, but especially because we don't have very good treatment mechanisms for it. But is that a problem? I guess it could be something to be taken into consideration, that this is a heavily trafficked, heavily maintained road area. Generally, what you'll see, if these are being used as more of a primary BMP, the areas will be much larger than the pavement. So hopefully that's not much of a concern. Or even that initial verge and grass filter or disconnection area up front can provide some of that treatment before it gets to the conservation area. Okay, moving along, as we move towards start to roll short on time, I'll have to start talking faster here. Sorry about that. But it's a grass swale. And so now we have a conveyance channel. And what we're trying to do here is move water slowly, again, at a very shallow depth. So this ends up being a broad trapezoidal channel with a wide bottom width, a flat slope that allows our low flows, which are the water quality flow per the permit, to travel within the blades of grass at a depth of roughly 4 inches or less. So we don't have a big river through here. And that means it moves slowly. It takes more than 5 minutes on sort of average to create residence. Average residence time creates that sort of 5-minute window, which allows for some soaking to occur. You don't have water just jetting through this like a stream, and which allows the credit to be given. And that is the residence time requirement. They could be oriented either way. You could have all the water coming in at the head of the channel, flowing sort of parallel to the general routing, or perpendicular, where water sheet flows and cascades along the length of the channel, in which case your residence time sort of becomes an average here, because you have water at the far end taking maybe 10 minutes, whereas runoff at the very end, which is almost at the catch basin, has about 0 minutes. So we, for credit purposes, say average is about 5. The only thing I want to point out with swales are that they, like any channel, if we're looking to just do our sort of cut and paste channels that I often see, something like on the upper right, just a quick V-shaped undesigned drainage channel, that really won't work. We'll have to incorporate some knowledge of open channel design to come up with to meet the criteria for flow depth and our shape. So it should look more like the grayish drawing on the left, with the trapezoidal given bottom width and a flow depth. This case, it's going to be very the water quality volume is not shown, just 100 year for their routing, which is what most people gravitate towards, but gets us looking like we should look. Our typical municipal or county mandated sections for roadways also generally show something like the lower right, which again is a V-shaped channel, which does a lot of good things but doesn't quite meet the standards. Also have to recognize that if conveyance is needed, that's great, but it's probably far more advantageous to use these as a bioretention area, because the credits for swales are so low. Okay, moving along quickly here. That was the tools. Let's look at this. Let's conclude here by talking about how we can apply these practices now. They were intended to be done as broadly as a low impact development strategy. So this is really unique. I just bring it up. The two neighboring communities here, you have not communities, but neighborhoods, neighboring neighborhoods that you have here just built exact same year. I thought that was very interesting. Again, low density, high density. The LID practices are more suited towards these low density type developments where you have disconnection, less impervious, less road width. Swales are readily able to be built in and disguised into the landscaping or even valued as landscaping features. But we have to recognize, I think, that the development model today more favors the bottom drawing, the higher density, quick drainage, curbs and gutters, catch basins, extra parking, high density development, and those are going to be a lot harder to fit to the runoff reduction processes in, because clearly, it goes without saying here, you see much less green space to use, and where there is green space, it's much smaller. So we'll probably have a much harder time and probably be, impractical on these higher density developments. So I did some numbers to try and maybe prove that they're economically the same, but it's hard to argue. The more density comes up to, in today's development models, probably twice the income is the upper subdivision. So I understand, and that's why we say this isn't a silver bullet. It won't be used everywhere. So where might it be helpful to those of you out here practicing as consultants on a myriad of types of projects? Parks and universities have a lot of green space. Individual residence projects see more and more of this that get caught up under the construction general permit because they disturb more than an acre, sometimes more than two, triggering post-construction requirements at times, or small subdivisions of these large lots. Golf athletic areas that end up triggering permit required over an acre. So again, lots of green space. Here where the runoff reduction practices could easily be fit into the landscaping, almost disguised, with minimal really change to the overall plans for the layout of the development. So then the next question you're probably going to ask is, what's necessary to do here as far as to use these practices? The spreadsheet needs to be utilized to calculate credits, and they need to be designed, identified on the plans, detailed in the plans, just like any other post-construction practice. By plans, I specifically mean the Stormwater Pollution Prevention Plan, or the SWIP. The spreadsheet is available. It looks like this. I'll work through an example of it here for you quickly. It can be found on our website. I just put this up there. I won't go through it, but because our website can be difficult to navigate at times, please call me or email me if you have problems finding it and downloading it. But these are the step-by-step directions you can go back to later. So let's look at an example of all this put together and close out with some realities here as I pass up my deadline here for time. This was an early application. So again, this is we're still a lot high on the learning curve, a lot of mistakes being done, but we're getting there. A little bit sort of trying to mimic an actual site here, an actual project, about 16 acres that were subdivided to 3 parcels for, again, large scale residential development. Desoils, and this was a little bit after the fact, after it was recognized that post-construction would be required. And the first step is with these, okay, where will we have houses and impervious cover? What are they going to be rough locations and sizes? In this case, they used maximum allowable impervious areas to sort of max out the build out of the lots, given their local regulations. And where's that water flowing from the disturbance in those impervious areas? In this case, the contours, although they look a little steep, I think the average grade was about 6%. They're uniform for the most part. They're straight down into a on-site and off-site channel. So the spreadsheet has 4 different tabs, and in this case, what was done is each lot was broken up into a different tab and calculated individually. Now, if this were more standardized development, maybe only one and needs to be done as a typical and not each individual house lot. We set that up, established the practice disturbed area and what the water quality volume requirement was going to be for that site. As I said, the slopes were a little bit steep for disconnection, so I showed them in blue, but we assumed that will still occur in order to get sheet flow to our filter strip and conservation area, but did not take credit for it. It wasn't needed for the most part. But then the filter strips in green and conservation areas in existing woodlands that were acting almost to buffer the stream were established for each lot there in the green and the brown. And the way you plug that in the channel is into the spreadsheet is first select the row for the practice we're using. So in this case, sheet flow to a grass filter strip on C&D soils. And we entered the practice drainage area. So both by impervious and pervious cover in terms of square footage, if that's a word, square feet. The next green box is the actual area of that practice. So what was the total acreage, or in this case, square footage of that grass filter strip? And then in the last green box, make sure we direct the filter strip to the next practice. Okay, in this case, we would have a conservation area to follow. So we'll drop down to the next row, which is in this case under 9, there's sheet flow to conservation area and C&D soils. The drainage area to that was the same. We just have this as just sort of the next practice down. So there's no additional drainage area in those first 2 green columns. The disconnection area, again, of the conservation woodlands is put in there, is about 1.25 acres. And at the bottom of the sheet, you'll see the water quality volume remaining from what the first slide showed is what was owed for this particular site. Shows a negative value, so we've well more than made up the difference of the water quality volume here. If that were positive 490, it's kind of ridiculously small, but that would be then what would be treated in the primary BMP. And then lastly, adding in, this is the part that we probably need to continue to put direction in. It seems to be some most challenging part, was all of this, then these expectations into the actual construction plans. So we had some notes made about disconnections being required, took language from the standard and put in there, actually using the old drawing and whatnot. But this is probably the challenge, is thinking of this, and I'll go backwards, in terms of a BMP to show you the sketches, and making sure we're identifying these practices, locating them on the plans, assuring that, again, moving backwards here for you, that these are actual areas that will receive the flow, not just circling areas that are high quality but aren't receiving any runoff. So we're attributing only the area receiving runoff from the site, and then including any other drainage area here in that calculation. The one thing I'll note as I kind of re-step through this is, this was a bit of a challenge, admittedly, that you have a convex sort of, or I should say, I just get those confused, more of a concave type scenario here, where you have a funneling situation, and all this runoff is really coming into maybe not being distributed as sheet flow, but coming really more of a concentrated area, although it's not really a channelized. And we had discussions about trying to even that out to help encourage this be more of a flatter terrain and provide more sheet flow into these areas. So we really should be avoiding that as much as possible. Okay, I'm a little over our time. It's about noon here, but just to wrap up quickly, it's a useful strategy. It may help in situations. It was designed to be an overall management strategy, but I think it can be helpful in places. They are low level. I mean, we're not designing rockets and spaceships here. These are grass areas. So the engineering is low level, but there's still effort involved in making sure that we're meeting the intentions and sizing them, and locating these areas and identifying them properly. And admittedly, we're still working out the kinks to this whole big picture concept and what we think could work to what are the realities and practicalities of construction, and especially transitioning from discussions and work done by the consulting engineers and site designers, and transmitting that and relaying that to the what ultimately happens by contractors and during construction. And that's a wrap for me. Hopefully I've left plenty of time for lunch for you. A few questions show up here in the chat. And does the, I'll see if I can work backwards until I get to one I've seen. Does the type of vegetation cover, cut grass, or prairie modify the credits shown? Well, that is a distinguishing factor. If it's cut grass or maintained lawn, that should be a filter strip. Prairie grasses that are not maintained, not mowed, outside of maybe occasional for maintenance, upkeep, invasive species, something like that. Those could be conservation areas. Much deeper root structure occurring, much more interception, higher quality of vegetation, you might say.
Well, thanks, Justin. It seems like you captured most of the questions during your presentation. We'll go through and take another look just to make sure that you got them all. And if not, maybe when we do a follow-up email to attendees, we could answer any questions that you didn't actually get to. Does that work?
That works well. Yes. And real quickly on the cost, that's something we like to do. It's just, it hasn't been, that would be very persuasive to be able to show the cost advantages. And there are some. Obviously, you're omitting catch basins, conduits, etc., from the cost of construction. But it would be good to lay that out at some point. Yes. Okay.
Okay, so just to wrap up, we want to thank our Ohio Stormwater Association sponsors, Davie Resource Group, Strand Associates, Butler County Stormwater District, and also Franklin Soil and Water Conservation District. If we do have some sponsorship opportunities available, if any of you or any of your companies would like to sponsor, please contact Kelly Kubander, our board president, if you are interested. Also, just another reminder, please, if you're interested, become involved with the Ohio Stormwater Association and one of our many committees. And some upcoming events. On October 27th, we have, in conjunction with OWEA, there's a watershed workshop, and it's taking place at the Embassy Suites in Dublin, Ohio, and we'll send out some information regarding that. And then we are planning to have the September and November webinars, and we're looking for some topics that would be of interest to all of you. So feel free to let us know if there's some topics that you would be interested in hearing more about. We also want to thank our host, Justin Reinhart, and the information. Thanks for the information that you've shared. We have Melissa Maneri with Ohio Department of Natural Resources, who is actually behind the scenes standing in for Dana today. And we want to thank WAMO for their support. So if there are no further questions, if you have questions, feel free to add them in the chat. But this concludes our webinar session for today. Thanks for joining.